Hello, thank you all for being here today, and thanks to the Committee of IEEE Sensors Conference, who allows me to present my research entitled Wearable Triboelectric Sensor for Respiration and Coughing Monitoring. My name is Vera. I am a PhD student under the supervision of Dr. Mehmet Yuce. We are part of the Sensor Technology Research and Development Laboratory at Monash University. Well, my presentation is organized as follows. First, I'm going to explain about our background review. Later, I will explain the sensor design and working principle and the different experiments performed for breathing and coughing monitoring in different scenarios and body parts. Today, the current crisis of the COVID-19 pandemic has put wearable sensor technologies in the spotlight of society more than ever, especially those technologies related with respiration monitoring. Apart from the respiratory affectations from viral infections, abnormalities in breathing can also indicate other chronic problems, and usually capnography is the non-portable gold standard for respiration rate monitoring. However, there are recent wearable alternatives that use sound, humidity sensors, body impedance, or fiber optical sensors to detect vibrations. On the other hand, cough is also a sign of infections and in daily life is one of the common causes for hospital visits and an indicator of possible respiratory problems. However, when we check the current state of the art, we observe a lack of technological tools for objective, unbiased, and accurate coughing monitoring of patients. In literature, as far as we know, compared to respiration monitoring, there are few real-time systems for coughing monitoring, using microphones, accelerometers, or piezoelectric sensors. Therefore, in the submitted paper for this conference, we have studied a new respiration and coughing sensor based on the emerging technology of triboelectric nanogenerators. The TENGs are getting popular in research due to their capability to work as both sensor and energy harvesters, as well as their versatility in design and manufacture, their low cost, and their flexibility. Unlike capacitive sensors, the TENG does not need a voltage bias, since it generates its own voltage. In the basic arrangement of a TENG, two electric layers contact each other, transferring opposing charges from one to another. This generates a motion-dependent current due to electrostatic induction once a load is connected to the electrodes. In the literature, there are few triboelectric sensors intended to monitor breathing rate and none, as far as we know, for coughing monitoring. Few of the triboelectric transducers for respiration are bulky for long-term use and are not completely portable since the electronic processing circuit and the transmission system are not yet integrated with the transducer as one same package. Our group at Monash University has some experience in the development of triboelectric sensors as human-machine interfaces, eye motion sensors, and Parkinson's disease sensors. Thus, the design we are going to present is an integrated wearable solution where the printed circuit board, or PCB, is an essential part of the triboelectric arrangement itself. In our design, the PCB and the sensor are integrated in one package. The dielectric layer, made by EcoFlex, is attached to the PCB by two elevation stripes of polyurethane foam to obtain a separation gap between the dielectric and the aluminum electrodes in the bottom part of the PCB. Notice that the triboelectric effect is between the aluminum and the EcoFlex. When they contact each other, negative charge is transferred to the dielectric. When there is no motion and the layers have maximum separation, there is no electric current through the resistor, but when the negative dielectric layer approaches the electrode, it pushes electrons to ground, generating a current and a negative voltage. The continuation of the motion allows contact between the dielectric and the electrode, transferring opposite charges once again, and when the layers separate, electrons move back to the conductor in opposite current, generating a positive voltage until they reach maximum gap distance, which is 3 mm as shown in the last figure. The observed integrated circuits in the top view of the PCB are operational amplifiers whose cascade configuration possesses a high input impedance stage of about 10 megaohms, necessary to match the high output impedance of voltage sources like TENGs. We have a cutoff frequency with a low-pass filter close to 10 Hz. There is also a notch filter stage to reject the electric grid frequency of 50 Hz and a negative gain amplifier with all the board working with 3.3 volts supply. Additionally, the sensor signal is sent to a computer using BLE technology. In the last figure, you can see the sensor attached to a hook and loop adhesive and an elastic band to place it in different parts of the body. So, in the first experiment, we placed the sensor in the elastic band on top of the user's t-shirt. The elastic band is well fitted around the body and the sensor is firmly attached to the band so that the chest can move the ecoflex layer of the transducer. Slow normal respiration with a low range of chest motion generates a low voltage signal, recognizable over the electrical noise as seen in the left figure. The duration of the respiration process, counting inspiration and expiration together, takes about 1 second. The time between two breath cycles is about 3 seconds, which can be extrapolated to 20 breaths per minute within the breathing normal range. In the last figure, we can observe difference between fast, deep breathing and slow, soft breathing. Deeper respiration generates greater amplitude of 600 millivolts peak to peak, which is expected due to the more significant range of movement. In the second experiment, the sensor is placed on the upper part of the abdomen, as shown in the right figure. We can observe that voluntary coughing action when the individual is sitting shows that the sensor is sensitive to slow cough rates. In faster coughing with higher intensity in the green square, the signal shows a waveform with greater amplitude and frequency and more peaks per cough. An explosive or intense coughing event shows even more peaks per cough and higher frequency. When the person is standing, soft and strong cough are also distinguished by the signal's amplitude and frequency. We can also see here more than 2 peaks per cough as the intensity of the action increases. Finally, the last figure, the difference between a simulated soft and intense coughing event in the red rectangle while the individual is walking can be appreciated, meaning that there is no significant influence of the overall body movement in the signal. We can also see that the change in amplitude for this case is not as noticeable as it was when the person was seated. In another experiment, the sensor was placed around the neck. The signal in the left image, when the person is seated, successfully shows a voltage output for soft, low-rate coughing action. However, it is evident that the voltage is lower than the one observed when the sensor was in the upper abdomen in the past slide. The amplitude for strong, fast coughing and intense coughing shows greater value and more voltage peaks than the resultant from voluntary soft coughing, as happened in the past experiment. But now intense coughing voltage is greater than strong coughing voltage. The existence of more than one voltage peak in the waveform of single cough may be a consequence of a bouncing motion of the device. We also see that the last image depicts differences in amplitude, waveform, and frequency between soft, strong voluntary coughing when the person was walking, but the black rectangle in the image shows a short disconnection of the battery cables due to the overall body movement, but there is a fast reconnection of the system after that, which of course can be improved by soldering the battery cables. Finally, another test was performed by directly observing the triboelectric signal due to the inhaled and exhaled air on the sensor. The triboelectric sensor is located under the nose without touching the mouth or other body parts except for the hand that holds the sensor. When breathing softly and slowly in front of the sensor, the inspiration and expiration actions are recognized. We can observe in the bottom figure 7 slow breath cycles in 20 seconds, which are approximately 17 breaths per minute. We can also discriminate from the signal fast breathing of 68 breaths per minute, with a higher frequency and similar voltage amplitude as the soft, slow breathing. In contrast, deep breathing in the red rectangle possesses a low frequency but a slightly higher amplitude. Interestingly here, the airflow is not enough to generate a movement of the ecoflex layer. Thus, the output of this particular experiment is not because of the mechanical triboelectric effect, but due to the motion of charged particles when breathing in and out of the sensor gap. In the air we breathe, there may be positive or negatively charged ions from the environment. In the right image, we see that the net electric field outside the imaginary Gaussian surface is negative due to a higher concentration of charges in the ecoflex layer than in the smaller aluminum electrode in the PCB. When the person breathes in closer to the device, the negative electric field probably pushes more negatively charged particles, the red circles in this case, towards the nose, leaving a more electric positive space that attracts electrons to the conductor from ground. When the person breathes out, the airflow contains positive and negative ions, for example, sodium, magnesium, calcium, or chlorine. The positive ones, the green circles in this case, are probably attracted by the negative dielectric layer, while the negative ones go closer to the conductor and push the electrons back to the ground, which explains the alternating voltage output in harmony with the breathing dynamic. Hence, to exploit this interesting observation, the sensor is attached to a face mask where we can see slow breathing of about 20 breaths per minute in the green square, soft, fast breathing in the blue square, and a high voltage, deep breath where inspiration and expiration are easy to differentiate. To sum up, we presented before an integrated small wearable triboelectric solution and demonstrated its sensitivity to breath and cough motions in different body parts. As far as we know, it is the first coughing detector based on TENG and is capable of detecting different coughing levels while sitting, standing, or walking. Finally, the sensor proved to be sensitive to charged particles in the airflow generated when breathing, without the need of a mechanical motion. This is something that should be analyzed in the future, as well as more appropriate signal processing tools and hardware improvements for long-term use and stability. With this, I conclude my presentation and thanks very much for listening. If there is any question, you can let us know in the emails at the bottom of the screen. Thank you.